If you've ever studied matrices before, then you're probably familiar with these formulae on screen here. These are the formulae for calculating the determinant of a 2x2 and a 3x3 matrix. But what about the determinant of a 3x2 matrix, or a 1x3 matrix, or a 20x30 matrix? How would you calculate those? Every single matrix encodes a linear transformation, that is, some kind of rotation, reflection, scaling, or shear. And this determinant is the scale factor of the transformation. If you start with a shape with area or volume x and you apply the matrix transformation, you end up with a shape with area or volume det m times x. And this scaling only really makes sense if you compare like with like. You can compare an initial area with a final area, an initial volume with a final volume, but it wouldn't make sense to compare an initial volume with a final area, because those are just different measurements. So mathematicians made the logical choice to only worry about the determinants of square matrices, the ones that map points from an n-dimensional space to another n-dimensional space. And thus all the other lesser rectangular matrices, those that mapped points from an n-dimensional space to an m-dimensional one, were left to gather dust determinantless. Until now, because today I'm going to show you how you can calculate the determinant of any matrix, starting off with 3x2s. The main reason this matrix supposedly doesn't have a determinant is because it maps points from 2D to 3D. So we go from a 2D area to a 3D volume, and those are incompatible, right? Why don't we try actually transforming a shape, and I'll show you why this assumption is wrong. We start in 2D with a unit square with its vertex at the origin, and we apply our 3x2 matrix, getting this as a result, a list of 4 new vectors in 3D. And if I plot them like so, you might notice something interesting. These points don't seem to be forming a polyhedron. It kind of still looks like a quadrilateral. And this isn't just a trick of perspective. All of these points do lie on a single plane, which means that the shape is still 2D, so it still has an area. This will happen no matter what 3x2 matrix you use, because of how matrix transformations work. When you apply a matrix transformation, what you're doing is you're changing the basis vectors. That explanation isn't very illuminating though, so let's return to normal 2D space for an example. In normal 2D space, the two basis vectors are 1, 0 and 0, 1, which we can describe as right and up. Furthermore, every single point in 2D space is a linear combination of these two vectors. The point 2, 3 is 2, 1, 0 plus 3, 0, 1, and the point -4, 1.5 is -4, 1, 0 plus 1.5, 0, 1, and so on and so forth. Now look what happens to our basis vectors when we apply the matrix 2, 0, 0, 2. Our 1, 0 becomes 2, 0, and the 0, 1 becomes 0, 2. If you move 2 right and 3 up now, you end up at the point 4, 6, but you still only moved 2 right and 3 up. It's just that the definitions of right and up changed. In other words, you can think of a matrix transformation not as transforming points in the plane, but instead transforming the plane itself and dragging all of the points with it. This is precisely what happens when we apply our 3x2 matrix. The basis vectors change and now have a z component, a depth to them, which means that the Cartesian plane is schmooved around and embedded in 3D space, but it's still a plane. So the points within it still form a shape with an area, not a volume. So the entire notion of a determinant, which we're taking to be the scale factor, is still valid. To find what the new area of the unit square is, with this example of 2, 1, 1, 0, 3, -1, we're going to use some geometry and some vector facts. So this is the shape we're finding the area of. It's a parallelogram, so what we can do is split it into 2 congruent triangles like so. Then to find the area of a triangle, we can just do a half AB sine C, where A and B are these lengths here, which are the magnitudes of our 2 basis vectors. Then for sine C, we can use a rather niche fact about the cross product, and that is that the magnitude of A cross B equals the magnitude of A times the magnitude of B times the sine of the angle between them, i.e. sine C. So we calculate that sine C is root 27 over root 28, and putting it all together and multiplying by 2 to get the full area, we get that the determinant is 3 root 3. Let's generalize this for a 3x2 matrix A, B, C, D, E, F. This first length here is going to be the magnitude of vector A, C, E, and the second length is the magnitude of B, D, F. And the sine C bit will be the cross product divided by the magnitude of ACE times the magnitude of BDF. So when calculating the area, a lot of this cancels, and we get that the determinant of a 3x2 matrix is equal to the magnitude of the cross product of the two new basis vectors. Cool, now let's do the 4x2 matrix. So we do the same sort of thing, do the magnitude, then for the angle we do... There's now a slight problem, in that the cross product only exists for vectors representing points in 3D, not 4D. So how are we going to do it? Well... here is the formula for the cross product for two generic vectors. Now, one way you might have learned this is that you cover up the top row and take the determinant of the resulting 2x2 matrix, and then cover up the middle row and take the determinant of the remaining 2x2 matrix, but stick a minus sign in front of it, and then finally cover up the bottom row and compute the determinant of the final possible 2x2 matrix. But there's a... Please stop interrupting. But there is a slightly different way to think about it, and indeed about determinants in general. If you look at all 6 of the terms involved in the resulting cross product, you'll notice that we have all possible pairs of elements that aren't in the same row or column. So for example, we have AD and AF, but not AB, AC, or AE. And then what we've done is group together the terms such that those that come from the same submatrix, as it were, are combined together. And this is exactly what happens when you have a square matrix, but there the only submatrix is just the entire 3x3 itself, so we just combined all 6 possible terms into one. So that leaves one final question. What's the rule with the minus signs? To explain that, we can play a fun, relaxing game. We start with our first combination, the main diagonal here, AEI, and we say that this term is positive. Then we switch the middle and bottom choices to get a new term, AFH. And because one switch was required to get there, this one will be negative. Then we can switch the top and middle to get CDH. It's taken 2 switches to get here, so it's going to be positive. We can play on, swapping adjacent rows with each other, and whenever the total number of swaps is even, the term is positive, and when it's odd, it's negative. That gives us the 3x3 determinant, or to make it fit in with our new discovery, a vector whose modulus is the determinant. In this case, they happen to be the same thing. So we can take this approach when trying to calculate the determinant of a 4x2 matrix. We take this as our leading diagonal and we play the long swapping game. In this case we end up with a vector with 6 elements. That's just because there are 4 choose 2 possible 2x2 matrices and each element has 2 terms. Then we square each element, add them together, square root, and ta-da, that's it. Or is it? Because I haven't proven that this is the pattern, it sort of just seems right. So why don't we try an example, we'll solve it 2 ways and see if the answers match. This is our test matrix, which turns a unit square into these points in 4D. But remember, these points all lie on the same 2D plane, so they still have an area. Now if we use the dot product to compute the angle between these two vectors, we get that cosine theta equals half, so theta is 60 degrees. The area of this shape is 2 half AB sine C, which is 2 times half times 2 times 2 times sine 60, which is 2 root 3. Then if we use the determinant method, it takes a little bit, but we get this vector, and sure enough, it has modulus 2 root 3, so our hunch is correct. And that means for tall matrices like this, I believe we have found the general algorithm to calculate the determinant. Ignore as many rows as you need to get a square matrix, and then calculate the determinant of that submatrix. Then repeat this for every square matrix possible, making each new determinant the next entry in the big vector. Then make sure to assign the signs properly based on the number of swaps, and finally calculate the modulus of the vector to get the overall determinant. So we're halfway there now, it's time to move on to the wide matrices.
Dans mon esprit tout divague, je me perds dans tes yeux, je me noie dans la vague de ton regard amoureux.
Yeah, the determinant is always going to be 0, because these matrices all represent transformations from higher to lower dimensions. When this happens, the original measurement in the higher dimension doesn't exist in the lower dimension. For example, the volume of a unit cube transformed into 2D space would be 0, because the idea of volume just doesn't exist in 2 dimensions. So the general rule for wide matrices is that the determinant is 0. Well, that was really underwhelming, so instead let's look at Bro, I was going to say that, just give me like 3 seconds to finish my sentence. Whatever. Inverses get really funky with these rectangular matrices for a few reasons. The very first one is that the side you apply the inverse on affects what the inverse actually is. Now with square matrices, this doesn't matter because both matrices represent transformations from n dimensions into n dimensions. But looking at this example here, this clearly isn't the case. The transformation on the right represents going from 2 dimensions up to 3 and then back down again, whereas the one on the left represents going from 3 dimensions down to 2 and then back up again. Let's expand the example on the left and see what we get. It's going to be a 3x3 matrix with these terms here, which by the definition of an inverse need to equal the identity matrix, leading to 9 simultaneous equations. Well, actually 3 sets of 3 equations in 2 variables. And I'll leave it to you to verify it, but these equations will always be inconsistent. If we focus on the leftmost column, the coefficients on the middle and bottom terms have to be multiples of each other, otherwise these expressions can't both equal 0. But that means that in the middle column, the middle and bottom terms have to be equal, which is impossible as one of them should be 1 and the other one be 0. And so no inverse exists. This should make sense because the mapping from 3D to 2D is many to 1 because there are infinitely more points in 3D than 2D, which would mean that the inverse would need to be 1 to many, and this is impossible for a matrix. Now turning our attention to the example on the right, we see that we get a 2x2 matrix, and then we equate this to the identity matrix to get 2 sets of 2 simultaneous equations in 3 variables. If I go ahead and solve this, instead of getting numbers for our unknown variables, we instead get equations of planes in 3D, which then intersect along one single straight line. This means that there are infinitely many inverses for our original matrix. This is less intuitive, but I guess what it's saying is that there are infinitely many ways to collapse 3D space into 2D space, whilst making sure that one specific plane is mapped to the XY plane. If you repeat this with a 4x2 matrix, you'll again find that there is no right inverse, and for the left inverse, you get 4 equations, each with 3 variables, which I assume would be solid 3D surfaces in 4D space, which would intersect to give solutions defined by a 2D plane. This leads me on nicely to the final part of the video, the I believe that when you have a matrix with m rows and n columns, the values of the elements in the left inverse matrix are defined by an m-n dimensional object. And this explains everything. This means that the tall matrices have inverses defined by lines or planes or higher dimensional objects since they have more rows than columns, so have infinitely many inverses. It also means that square matrices have inverses defined by 0-dimensional objects, as in just points, since they have the same number of rows as columns, so have unique inverses. And it means that wide matrices have inverses defined by objects in negative dimensions, which of course don't exist, and so they do not have inverses. So there we go, now you can calculate not only the determinant, but also the inverse of any matrix. I don't really know if what I've come up with counts as a real determinant, or if it fails to satisfy some condition I'm not aware of. I really want to see if I could solve this problem by myself, and thus I have not checked for any existing literature on the matter. Hopefully my result isn't widely known or just flat out wrong, but even if it is, I hope you learned something new from this video, and thanks for watching.